Okay, we're going to do operations with polynomials. This is the 5.1. So you'll remember polynomials have non-negative exponents. Okay, so you're probably wondering, well, aren't they all non-negative? And we're going to show you what a negative exponent does pretty soon. But that would then make it non-negative, so not a polynomial. So you'll notice the polynomial example I've given you here has only positive exponents, or in the case of the 7, you could imagine it has a 0 exponent. That's why I had to say non-negative, because you could imagine this was x to the 0, because of course anything to a 0 power is just 1. So that's why we have to say non-negative. Okay, then of course the other idea is this degree of a polynomial is the highest power on any given term. So we're looking here at the highest power 3, so this one degree is equal to 3. So it is always the highest exponent. Alright, and of course we have to put in the standard form where you have decreasing powers of x. Okay, so if I wanted to rewrite this one, you're going to start with the negative 5. Remember, the negative stays with that 5, plus 2x squared minus 7, I don't need to x to 0, plus 3x. So if we looked at these expressions, could we decide if they are a polynomial? And I would look at the first one and say, no, not a polynomial because it has a negative exponent. I'm going to look at the second one, 3 minus square root of x, and say, no, it's not a polynomial because of the radical symbol. And as we'll learn later, the square roots or any radical is really a rational exponent. It's fractional, not integer. So then I'll look at the next one and say, yes, it's a polynomial. It is of degree 4. And I might even go further and say it's a binomial. So I'm going to say it is a 4th degree binomial because there are 2 terms. Okay. And then the last one I'm going to say, yes, it is a polynomial. 2 variables, so the highest exponent you actually have to add them together. So imagine this is a 1, and so this is a degree 6. So there's no name for degree 6, you just say it's a polynomial of degree 6. Okay, now we've been doing this for a long time, but let's try and be a little bit more explicit what we're trying to do when we're simplifying polynomials. You want to make sure there are no parentheses, there are no negative exponents, okay? And we are going to make sure that you've combined all like terms. And like terms is something we've talked a lot about. So let's start talking about how you simplify when you multiply and divide with just a monomial. Oops, sorry for the interruption, I'm back. I think I was saying we're going to multiply and divide monomials. Okay, so only a single term here every time we do this. So of course the old rule, so gosh, we know this one. X to the a times x to the b is equal to x. It's an x to the a plus b. Got that every time. And it really doesn't matter what a and b are, okay? They can be almost anything at all. So, but then you have this other rule you were taught, x to the a over x to the b is equal to x to the a minus b. Now, we could always, well, let me go back to this, hold on. This is an equal sign, okay. We can always write x to the a minus b as x to the a plus a negative b. Okay, those rules we have. And so this could be x to the a times x to the minus b. Is another way to write that. Okay, so now I've got that, which came from, if we just complete the circle of where we came from originally, let's just put these side by side, x to the a over x to the b. Of course, the x to the a's cancel each other, leaving a 1, right? So what we've come up with is our own spanking new rule that x to the minus b power can be the same as 1 over x to the positive b value, and this is what we really want to take away from all of this. Okay, this is the most important thing to remember, that if you have a negative exponent, it means take a reciprocal. Okay, you get a fraction instead, or you go from the numerator to denominator, and you lose the negative on the exponent. Let's just do a couple of examples if you're asked to simplify. The first one, 2x is raised to the negative 3 power. The negative 3 actually is only on the x, okay, only on that variable x. It's not on the 2, okay? So this is going to simplify as the 2 stays where it was in the numerator, but the x has to change to a denominator, and it keeps its 3 exponent, but now it's positive 3, okay, because it went from a numerator with a negative to a denominator with positive. And on the same idea on the second one, if we're simplifying this one, all we can do is move. This one has a negative exponent, so it's going to move. It's kind of like an elevator. I still have the over 3, but now x to the 4th has rode the elevator, used up the minus sign like its ticket, and now it's in the top numerator. Okay? So those would be how you simplify those negative exponents so that they are positive exponents. And for completeness, let's finish our properties of exponents. You've seen these before. If you have a variable with an exponent that is raised to another exponent, that's multiplication of the exponents. So x to the a times b. The difference here, there's only one base, right? Then we can talk about what happens if you have x and y, kind of a product here of x and y, in parentheses raised to the a, so that that exponent a is on both the x and the y. They're separated by multiplication, so it's a simple matter to give them both the a. They can unshare the exponent, and they can each have it to themselves. And then, of course, the same thing happens when you're talking about division. They both get the exponent. Okay, so that satisfies that. And then, of course, our favorite one, we talked about this, x to the 0 is equal to 1 by definition. Okay, so don't ever forget that. And that's a really cool thing. You can have this terribly complicated thing, and as long as I raise it to a 0 power, the whole thing is 1. Here's an example for you to try. Go ahead and pause it. Make sure you can get the right answer by coming back and checking with mine. And to explain what I did, and first let me say that there are many different ways to get to the same right answer. There isn't any particular order that's required. So I chose to sort of combining, if I had the same base, let me add those exponents together first. Okay, and that was my choice. And then I took care of the negative exponents last. Okay, if you had done it in a different order and got the same answer, everything's great. The last example I'm going to ask you to do is, I'm going to have n squared over n to the 10, of course, probably the last skill we haven't done yet, and of course you would get 1 over n to the 8th power, and if I wanted to write that so it wasn't in a fraction, I could have called it n to the negative 8, which of course is exactly what you would get if you had just started from the beginning and said, well, I'm going to write n in the top, so I'll do 2 minus 10 and get negative 8. Okay, so either way works, and we get a good answer. Okay, we'll spend a minute talking about dimensional analysis here. And you know how we're always doing you throw a taco up in the air with an initial velocity, and I'm sort of always struggling with what would be a good initial velocity. What would be typical for you or me to be able to throw a taco with. So it occurred to me, well, why don't we just, I know a lot of pitchers in Major League Baseball can throw in the 90 miles per hour. So I picked a number, 96 miles per hour, and let's see what that would be in feet per second, okay? So the way to do this is to start with what you know. I have 96 miles per hour, and let's start changing up the units, okay? Just make the units work for you. So I started with that, and I'm going to times, I need to get rid of the miles, for example. So let's put 1 mile on the bottom. 1 mile is 5 tomatoes feet long, okay? 5 tomatoes, so that comes out to be 5280 feet. Okay, so that's that. So now my miles have canceled. So I've already got my feet, and then I have to worry about the hours. I have 1 hour that I'm going to want to cancel with that one. So 1 hour is the same as 60 minutes. And I have a minute to get rid of, so 1 minute is the same as 60 seconds. My minutes will cancel, and if you notice, what is the units that are left? I have feet and seconds that are the remaining units, so my answer when I multiply this all together will be feet per second. So let me do that real quick. Okay, so there you have it, 140.8 feet per second. And now I have a challenge for you. So your homework, and if you want to email me your answer, your work and everything, that's fine. But I want you to answer the question, how much or how many dollars, so make sure it's in dollars for me, how much does it cost to drive your car or your favorite car or your parents' car, whatever you want to do, from HRA to Palm Beach, Florida. So what you're going to need to do is, you want your thing to end up with dollars. Now let's do it this way. So you might start there, and then everything else is going to be dimensional analysis, right? Something, something, something. You're going to need to do a lot of Google searching. How far is it? I don't want to give away too much. I want you to try and figure it out as much as possible. But you're going to need to know some information about your car. You're going to need some information about your local gas station and things like that. So do some Google searching, find the numbers you need, and figure out how much it would cost you to drive from HRA to Palm Beach, Florida. Good luck.